What's up guys, this is Masi, welcome to my channel. In this video I want to talk about section 7.4 from chapter 7, from unit 7 of Chemistry 12 by Nelson. And the section is about qualitative changes in equilibrium systems. So imagine that your friend is trying to stay in the same place while walking up an escalator that is moving down. She will be able to maintain her location if the rate at which she walks up equals the rate at which the escalator moves down. As long as the rate your friend walks up is the same as the rate that the escalator moves down, this system is in a state of dynamic equilibrium. However, should the escalator begin to move faster while your friend maintains the same rate of walking up, the dynamic equilibrium will be disturbed and the location of your friend on the escalator will shift down. To reestablish equilibrium, she must increase her stepping rate to match the new rate of motion of the escalator. However, when dynamic equilibrium is reestablished, she will be at the new location, lower on the escalator. As we will see, the changes in this dynamic equilibrium are analogous to what happens in the chemical equilibrium system when it is disturbed. What do we mean when we say a chemical system at equilibrium is disturbed? Previously in this chapter, we saw that changes in temperature can shift the position of an equilibrium in a closed system. These changes are examples of disturbances in a chemical equilibrium system. In general, chemical systems at equilibrium may be disturbed by changes in pressure, temperature, concentration, or a combination of this. Le Chatelier's Principle. In 1884, the French chemist Henri-Louis Le Chatelier was best known for his work in analyzing chemical reaction systems at equilibrium. Le Chatelier started with a well-defined initial equilibrium state, then changed one property of the system. He observed that there would be a temporary non-equilibrium state in a chemical reaction system, and then a new equilibrium state would become established. The goal behind Le Chatelier's investigations was to maximize the yield of products from equilibrium systems, using the systematic process of trial and error. As he gathered data, he saw a pattern emerge. He communicated this pattern to the scientific community as the generalization now known as Le Chatelier's Principle. So when a chemical system at equilibrium is disturbed by a change in a property, the system adjusts in a way that opposes the change. So it's gonna the system will adjust itself to basically damp that kind of changes. So let's read it here. Le Chatelier's Principle, a generalization that states that chemical systems at equilibrium shift to restore equilibrium when a change occurs that disturbs the equilibrium. Le Chatelier Principle allows chemists to predict the qualitative effects of changes in concentration, pressure, and temperature on a chemical reaction system at equilibrium. Since Le Chatelier's time, this generalization has been supported through extensive evidence. It is regularly applied by chemical engineers who want to maximize the yield of the desired product to make industrial-scale chemical processes more efficient. In fact, Fritz Haber and Carl Bosch used Le Chatelier's Principle in their work to devise a process for economical production of ammonia gas from atmospheric nitrogen. Le Chatelier's Principle and changes in concentration. An adjustment by a system at equilibrium that results in a change in the concentration of reactants and products is called an equilibrium shift. One way to cause an equilibrium shift is to add additional reactant to the reaction vessel. By applying Le Chatelier's Principle, we can predict that increasing the concentration of reactant will shift the equilibrium to the right to oppose this change. The prediction can be tested by investigation. For example, when a light yellow solution of iron 3 ions is mixed with colorless solution of thiocyanate ions, SCN minus, and equilibrium is reached with the product iron thiocyanate ions. The balanced chemical equation for this chemical reaction system is, as you see here, we have it like that. Note that there are two reactants and one product in a forward reaction, and this equilibrium for forward reaction of this equilibrium system. Figure 2 shows the concentration of the reactants and products over time. As the 0 time points, the two solutions are mixed. Notice how the concentration of reactants fall as the concentration of the product increases. So as you see here, that's how it falls. These are the reactants, and the product is FeSCN2 2+ is going up. Now, how the concentrations of reactants fall as the concentration of the product increases. When this reaction system reaches equilibrium, all three concentrations remain constant and all three lines on the graph are horizontal. At the point marked by the first dotted vertical line, more thiocyanate ions are added to the equilibrium. This causes the solution to change color. After the addition, the concentration of thiocyanate briefly increases, then it decreases again. The decrease is a result of some of these ions being used to form more product, the iron thiosulfate thiocyanate ions. Similarly, the concentration of aqueous iron 3 ions decreases as some of them are used also in product formation. However, eventually equilibrium is reestablished at a new position. So as we see here, we have three sections. We went through the first one. For the second one, it says when yellow aqueous iron 3 ions initially mixed with colorless aqueous thiocyanate ions, a portion of these ions combine to form red aqueous iron thiocyanate ions. As the reaction progresses, the concentration of reactants fall as the concentration of the product rises until equilibrium is reached, when more thiocyanate ions are added. At the point indicated by the dashed line, the aqueous thiocyanate ion concentration increases momentarily but then falls off as additional aqueous iron thiocyanate ions are produced. So as you see here, we have a sudden jump here and sudden jump here. So we increase the concentration of thiocyanate ions, so that's why the equilibrium is changed for all of them, and in order to damp this increase in concentration, the reaction shifts to the right. It shifts to the product side. So as you see here, we have a jump more in SCN2+ is increasing, and we have decrease in Fe3+. So that's basically the change you will see as we increase the concentration of SCN-. After the addition, the concentration of thiocyanate briefly increases, then it decreases again. The decrease is a result of some of these ions being used to form more product, the iron, which are the iron thiocyanate ions. Similarly, the concentration of aqueous iron 3 ions decrease as some of them are used also in product formation. This experiment verifies the prediction made by Chateliers Principle that increasing the concentration of a reactant will shift the equilibrium to the right. Notice that the concentration of reactants and products at these new equilibrium positions are different from their concentration in their original position. So as you see here, the equilibrium concentration here and here is different from what you see in these two, and the equilibrium concentration of the product is different from the old equilibrium condition. Notice that the concentration of reactants and products at these new equilibrium positions are different from their concentration in the original equilibrium. When additional reactant is added, the equilibrium concentration of the added reactant in the new equilibrium is usually higher than was its equilibrium concentration in the original equilibrium. Le Chatelier's principle also predicts that removing some of the reactant in the chemical system at equilibrium will shift the equilibrium to the left. It means that toward reactants to partially counteract their lower reactant concentration. We will look at these predictions more closely by considering an investigation of the chemical reaction system represented by the following chemical equation. 2CO2 gives 2CO plus O2. When more carbon dioxide, so basically what we have here, carbon dioxide is the reactant and carbon monoxide and oxygen are the products. When more carbon dioxide gas was added to the system at equilibrium, its concentration first spiked, then immediately started to decrease as the concentration of the product increased. The concentration of gaseous carbon dioxide, carbon monoxide and oxygen at the new equilibrium position are higher than they were in the original equilibrium. So as you see here, the reactant is decreasing and the products are increasing until we reach the equilibrium condition, and all of a sudden at the equilibrium condition we started to add more of this carbon dioxide, so we have a jump in initial concentration of carbon dioxide and then starts going down, and we have a jump for concentration of CO and O2. So when one of the products, carbon monoxide, was removed from the system at equilibrium, more reactant was converted to products to compensate for the change. So that's the second case. In this case, again, in the first part we have the same thing. The concentration of reactant is decreasing and the concentration of products are increasing to equilibrium condition, and all of a sudden we remove some of the products from the reaction system. We remove the CO, so the concentration of CO is reduced dramatically. So as you see here, when one of the products, carbon monoxide gas, was removed from the system at equilibrium, more reactant was converted to products to compensate for the change. The equilibrium shifts to the right, the concentration of the oxygen gas increases while the concentration of carbon dioxide gas decreases until a new equilibrium is established. So as you see here, when the concentration drops, the concentration of this one, when it drops, the reaction is gonna approach to the right side. It's gonna shift to the right side. So more products are producing and we have less of the reverse reaction. So that's why we have reduction in CO2 concentration, and we have concentration increase for CO and O2. Collision theory and concentration changes in an equilibrium system. According to collision theory, entities in a chemical system must collide to react. When the concentration of an entity in a chemical reaction system is increased, it is more likely that an entity will collide with other entities. So that's obvious. So when we increase the concentration of an entity, the possibility of having collision is more with other entities. There are simply more of them present. However, only collisions between reactant entities can potentially contribute to a chemical reaction. Even so, the more frequently collisions occur overall, the more likely it is that the chemical reaction will take place. So basically, we need to have more collision with enough energy. Otherwise, we will not have any chemical reaction. Chemical collision theory explains the response of a chemical reaction system at equilibrium to a change in concentration as a result of random collisions and probability. When we add more reactant entities in the equilibrium system, the equilibrium shifts to the right because the number of successful collisions for the forward reaction increases. If instead we add more products entities, then the number of successive collisions for the reverse reaction will increase and the equilibrium will shift to the left. That makes sense. So when we increase the concentration of the reactants, because of the collision theory, the reaction shifts to the right, and whenever we increase the concentration of products, we have more collisions for products, so the reaction will shift to the left. The rates of a chemical reaction reflects how often reacting entities collide, be they products or reactants. Therefore, when we add a reactant to an equilibrium system, the resulting higher concentration increases the rate of forward reaction to which it contributes, and the higher rate in turn decreases the concentration of that substance. So the forward reaction rate then decreases. Conversely, the product or the products of the forward reaction increase in concentration and so becomes more likely to collide, causing the rate of reverse reaction to increase. Once the rate of the forward and reverse reactions become equal, the new equilibrium is established. We have seen it before in other videos. The rates of the forward and reverse reactions will not be the same as in the original equilibrium, however. So we have the forward and backward or forward and reverse reaction rate. They are the same. So that's why we call it a equilibrium condition. So now let's see the applications of the Chatelier principle and concentration changes. Chemical engineers may all apply Chateliers principle when designing industrial processes based on reversible reactions. Often, the production process involves continuous addition of reactants or removal of products. This prevents the chemical reaction system from ever reaching equilibrium, so that the formation of products will always be favored. One example of this is in the industrial production of aqueous nitric acid, HNO3. So for example, we have 3NO2 plus H2O gives 2HNO3 plus NO. Nitric acid has many uses such as in the synthesis of fertilizers, explosives, dyes, and perfumes. Nitric oxide is not as useful in the industrial production of aqueous nitric acid. The nitric oxide gas is removed from the chemical reaction system by reacting it with oxygen gas. As the nitric acid product is removed, the equilibrium shifts to the right to compensate, so more reactants form products. This has their desired result of increasing the yield of nitric acid. Another example is the gasification of carbon. The chemical reaction system is an important part of the conversion of biomass to usable hydrogen gas fuel. At high temperature, elemental carbon Cs reacts with water vapor to produce hydrogen gas and carbon monoxide. The balanced equation for the gasification of carbon is C plus H2O gives H2 plus CO. Carbon monoxide gas then reacts with water vapor to produce gaseous carbon dioxide and hydrogen in a reaction known as water gas shift reaction. So CO plus H2O gives CO2 plus H2. As fast as the gasification reaction produces gaseous carbon monoxide and hydrogen, it is used up as a reactant in a water gas shift reaction. Thus, the water gas shift reaction constantly forces the equilibrium position of the gasification reaction to the right, producing more products. This has the effect of increasing the yield of the hydrogen. The Chateliers principle also applies to biological processes. For example, hemoglobin in your blood, Hb, binds to dissolved oxygen in a reversible reaction represented by the balanced equation. So Hb plus O2 is going to be HbO2. Oxygen is first absorbed into your lungs. The concentration of oxygen, a reactant in the lungs, is high, so the equilibrium position is to the right toward the products. Hemoglobin oxygen complex HbO2. The hemoglobin oxygen complex in the blood is then pumped to your body cells where the oxygen concentration is relatively low. In other words, the concentration of this reactant is low in your body cells. To compensate, the equilibrium shifts to the left in favor of the reactants. So as a result, oxygen is released from the hemoglobin and it is then available for use by your body cells. Now let's see the Chateliers principle and changes in energy. So let's have a quick summary. So previously we said the concentration of reactants and products can shift the equilibrium to the right or to the left. So when we increase the concentration of reactants, the reaction will proceed and will shift to the product side or to the right side. If we reduce the concentration of reactants, it will shift to the left, to the reactant side. We have the same thing for products. If we increase the concentration of any products, the reaction will shift to the reactant side and we will have lower yield. If we reduce the concentration of products or one of the products, the reaction will proceed to the right or proceed to the product side. So in this example, in the new section, I'm going to talk about Le Chatelier's principle and changes in energy. So a system at equilibrium will also shift when it is disturbed by the addition or removal of energy. For example, an equilibrium will shift when the temperature is increased or decreased. It means that we have a change in thermal energy. To apply Le Chatelier's principle and predict how a change in energy will affect the chemical system at equilibrium, we can think of energy as a reactant or a product. So we usually use Q or E as the reactant as a chemical compound for reactant side or product side. It is common to show it as part of the reaction. For example, energy is absorbed in an endothermic reaction. If we consider energy to be a reactant, we can write the word equation like that. So reactant plus energy gives products. So whenever we have endothermic reaction, we can write the reaction like that. So energy is going to be one of the reactants when we are talking about endothermic reactions. Similarly, since energy is released during an exothermic reaction, we can consider energy to be a reactant and write. So here it has to be a product. We consider energy to be a product and write like that. So whenever we have endothermic reaction, energy is going to be one of the reactants, and whenever we have exothermic reaction, since energy is released, energy is going to be one of the products. So to use Le Chatelier's principle to predict how an equilibrium will shift in response to a change in energy, consider how the system can counteract this shift. So basically we can say for endothermic reaction, as we increase the temperature here, or thermal energy, as we increase the temperature, the reaction will shift to the product side, will shift to the right hand side to damp this change. And whenever we have exothermic reaction, when we increase the temperature, when we increase the thermal energy, the reaction will shift to the left, to the reactant side. What about when we reduce the temperature? For endothermic reaction, when we reduce the temperature, we reduce the thermal energy, the reaction will shift to the left side, it shifts to the reactant side. And whenever we are talking about exothermic reaction, when we reduce the temperature or when we reduce the thermal energy, the reaction will proceed or will approach to the right hand side or the product side. So let's read this part about endothermic reactions. If an endothermic reaction is cooled, it means that thermal energy removed. We can consider that the quantity of one of the reactants has been decreased. We can therefore predict that the equilibrium will shift to the left toward reactants, and energy will be released. For example, the decomposition of dinitrogen tetroxide gas to nitrogen dioxide gas, NO2, is an endothermic process. We can represent the reaction by the balanced equation like that. So since it's endothermic, energy or thermal energy can be one of the reactants. If thermal energy were added to this equilibrium system by heating, the equilibrium would likely shift to the right, as we said earlier, because here we have endothermic process. When we increase the temperature, the reaction will proceed to the right or shift to the right. So if thermal energy were added to the equilibrium system by heating, the equilibrium would likely shift to the right. The additional energy would be absorbed to create more product, which is nitrogen dioxide gas. Since that nitrogen tetroxide gas is colorless and nitrogen dioxide gas is reddish brown, such a shift would make a gas mixture a darker color. Figure 5 shows the visible changes in this chemical reaction system when the temperature was changed from room temperature 0 or to 85 degrees Celsius. So as you see here in this picture, the room temperature sample in the center contains a mix of both gases. Changing the temperature shift the endothermic reaction equilibrium. The sample on the left at 0 is shifted toward the formation of colorless dinitrogen tetroxide gas. The darker color of the sample shift to the right at 85 degrees is due to a shift toward the formation of reddish brown nitrogen dioxide gas, NO2. Now let's talk about exothermic reactions. If thermal energy is removed from an exothermic reaction where energy is a product, then the equilibrium will shift to the right or toward the products, and energy will be released to counteract the change. If energy is added to an exothermic reaction, the equilibrium will shift to the left to compensate for the change, and the energy will be used as the products are converted to reactants. As an example of an exothermic reaction is the forward reaction in a reversible reaction in which sulfur trioxide gas is produced from gaseous oxygen and sulfur dioxide. The balanced chemical equation for this reaction includes energy is like that. 2SO2 plus O2 is going to be 2SO3 plus energy. So as you see here, energy is one of the products. It is exothermic reaction. So from Chatelier Principle, we can predict that removing energy will shift the equation to the right. So when we remove this one, the reaction will shift to the right to compensate for this change. When the reaction vessel is cooled, it means that we lower the thermal energy. The more energy will be released and more sulfur trioxide gas will be produced. Why? Because the reaction will shift to the right. As you see here in figure 6, cooling this system after it has reached equilibrium results in a new equilibrium being established at a lower temperature. So when temperature reduces, since we have exothermic reaction, the reaction will proceed toward the product side. So that's why we will have more concentration of SO3 and we have lower concentration at equilibrium for O2 and SO2. In summary, if energy is added to or removed from a chemical reaction system at equilibrium, the equilibrium shifts in the direction that will compensate for the change in energy. Now, so far we have seen the effects on and effect of temperature and concentration on equilibrium position. Now in this part I want to talk about the gas volume or pressure. Le Chatelier's principle and changes in gas volume. If you have ever used a manual bicycle pump, you know that changing the volume of a sealed container of gas changes the pressure of the gas in the container. Changing the volume of a container of gas also changes the concentration of the gases in the container. To understand how pressure relates to concentration in gases, first consider what happens to pressure when the volume of a gas changes. We will assume that our gas behaves as an ideal gas, which is a hypothetical gas that obeys all gas laws. According to Boyle's law, the pressure exerted on a container by a certain amount of an ideal gas held at a constant temperature varies inversely with the volume of the gas. You remember P times V is always equals to a constant number. This means that as the volume of the gas changes, its pressure changes too. When the volume goes up, pressure goes down. When the volume goes down, pressure goes up. In the case of a bicycle pump, decreasing the volume of the cylinder to 1/3 its original volume would increase the pressure threefold. Boyle's law holds true whether the container holds the pressure gas or a mixture of gases. However, when a container holds a gas mixture, each gas exerts its own partial pressure. The partial pressure of a gas is the pressure exerted by any one gas in a mixture, and is the same pressure as it would exert alone. The total pressure is simply the sum of all the partial pressures. When the volume of the container is changed, each gas in the mixture contributes its new partial pressure to the new total pressure. So when the volume of a gas mixture decreases, the concentration increases proportionally to the increase of their partial pressure. Figure 7 illustrates the changes that take place in a container of gas when the equilibrium decreases by half. The container is holding a mixture of gases that react according to the equation. So N2 plus 3H2 gives 2NH3. By Boyle's law, we know that reducing the volume of the container by 1/2 will double the total pressure of the gases in a container. Since the partial pressure of each gas will double, the number of molecules of each gas per unit volume also double. According to the balanced chemical equation, there are 4 reactant entities and 2 and 3 moles of H2 per unit volume for every 2 product entities, which is 2NH3. The total partial pressure of the reactants is twice that of the products. So when the volume of the container is reduced, the change in concentration of the reactants will be greater than the change in concentration of the product. Chateliers Principle predicts that the equilibrium reaction will shift to the right to reduce the total number of entities per unit volume in the container from 4 entities to 2 entities, which reduces the total pressure of the system. So as you see here, since the volume changes, the pressure changes as well. So as you see here, we have 3 pictures, A, B, C. The container holds an equilibrium reaction, N2 plus 3H2 gives 2NH3. As you see in the first one, the part B, it says the volume of the container is decreased by half, which doubles the total pressure of the system. And C, the reaction shifts to the right, which decreases the total number of particles in the container and the total pressure by producing more ammonia. So in this part, I want to talk about changing an equilibrium system without affecting equilibrium position. As chemists and chemical engineers strive for ever higher efficiency and productivity in equilibrium systems, they may be limited by how much they can change concentration, pressure, and temperature. However, it is possible to modify the amount of reactants and products using methods that do not change the equilibrium position. These methods include using a catalyst, adding an inert gas, and changing the state of the reactants. We will take a brief look at some examples of these methods. So now, instead of changing concentration, pressure, temperature that changes the equilibrium position, in this method we want to include the catalyst, or adding or removing inert gas and changing the state of reactants. So without changing the equilibrium position, we will see what are the effects or how we can get more yield or productivity. Now let's start with the catalyst. Earlier in your studies, you learned that a catalyst provides an alternative path for a chemical reaction that has a lower activation energy barrier. In a reversible reaction, catalyst increases the increase the reaction rates of the forward and backward reactions equally, since both reactants and products can form by the lower energy path. Therefore, a catalyst doesn't change the equilibrium position, and the final equilibrium concentration of the reactants and products are not altered. However, the reaction reaches equilibrium much faster, which can be very useful. So as you see here, uncatalyzed reaction, we have the red one, and for catalyzed reaction, we have lower activation energy. So the effect of the catalyst is to lower the activation energy of the reaction. It doesn't change the energy levels of the reactants and products, so the overall energy change is not affected. As a result, the position of the equilibrium is not affected. Inert gas. An inert gas is the gas that is not reactive and so will not enter into a chemical reaction. If an inert gas is added to an equilibrium system involving a gas mixture and the volume of the container is kept constant, the total number of entities in the volume and therefore the total pressure will increase. So when we have inert gas, we have total pressure will increase. However, the partial pressure of the reactant and products entities remain the same. Since there are more entities, there are more collisions, but collisions involving the inert gas will not result in a chemical reaction. These collisions can, however, redirect the movement of any entity involved. Imagine that the inert gas entities are fixed obstacles placed randomly in a container, like bumpers in a pinball game. The number and frequency of collisions between reactants and products remain the same, and the obstacles redirect reactants and products entities when hit, but do not change the frequency with which reactants and product entities collide with each other. As long as the collision frequency for both forward and reverse reaction is unchanged, equilibrium will not change. Next part is about state of reactants. When a chemical system involves entities in more than one state of matter, equilibrium is affected only by changes in concentration of entities that are in the same state of matter as the substances involved in the chemical reaction system. For example, consider the reaction of solid iodine vapor with hydrogen gas. So H2 plus I2 is going to give us 2HI. Sodium iodine is placed in the reaction vessel with hydrogen gas. The solid iodine sublimes. It means that passes directly to gas from solid phase before reacting with hydrogen. Once the system has come to equilibrium, the reaction vessel holds a mixture of hydrogen gas, hydrogen iodide gas, and solid iodine, provided there is some solid iodide present at equilibrium, and the gas phase will be saturated with iodine. That is, the second equilibrium will have been established between solid and gaseous forms of iodine. Adding more solid iodine at that point cannot change the amount of gaseous iodine, and consequently changing the amount of solid iodine doesn't affect equilibrium. So as you see here, since this one is in solid state, as we increase or decrease the concentration of iodine, it doesn't affect the equilibrium or equilibrium position. So basically, those chemicals that are on a different state, their concentration doesn't really change the equilibrium. So that is the end of this section 7.4. I hope you enjoyed this video. Please leave me a comment if you have any question, and I'll get back to you as soon as possible. And please don't forget to subscribe to this channel. Thank you.